Hello everyone, thank you for attending my presentation. My name is Miguel Mosteiro. I'm going to talk about supervised average consensus in anonymous dynamic networks. This is joint work with Dariusz Kowalski. Anonymous dynamic networks is a model that has attracted a lot of attention recently, where nodes do not have identifiers or labels. The motivation is that this type of network could be deployed as a massive monitoring infrastructure like a sensor network. And the dynamicity comes from the communication links assuming to be changing due to mobility failures or other factors. Let me describe specifically the model. We have a fixed set of end nodes without identifier or labels. The communication is synchronous. In each round of communication, a node broadcasts a message to its neighbors and receives the messages of all its neighbors, and then executes some local computation that is assumed to take negligible time. With respect to topology, we assume that each round the network is connected. The dynamicity in standard anonymous dynamic networks is given by the links changing arbitrarily, but this is maybe too pessimistic in practice. Indeed, good expansion topologies are the norm rather than the exception in practice. So for this work, we assume that it is known a lower bound on the isoperimetric numbers of the topology graphs. The isoperimetric number is the ratio between the number of links crossing a cut and the number of nodes in the smaller side of the cut. It's closely related to the conductance, and it's a characteristic of the expansion of the topology. With respect to the problem, fault-tolerant consensus has been studied for a long time in distributed computing. It can be defined as given a distributed system of n processors, all agree on a value and stop. In particular, for network, the problem called network consensus can be defined as given a network of n nodes, each holding an input value. Every node obtains the same function of those input values and stop. This problem has been very well studied in systems and control theory. Popular functions that the nodes obtain are average, sum, and maximum. We concentrate in this work in the average. The problem is clean, but applying that problem in a model like the anonymous dynamic networks is challenging. The question basically boils down to how to reach consensus in a crowd that is moving or is changing and without revealing the identity of every member. Moreover, the nodes are supposed to be low cost for the intended application. Therefore, startup failures and late failures may occur, so the number of nodes participating in the network are not necessarily known in advance. So what we study is the network average consensus in anonymous dynamic networks, assuming that the number of nodes is unknown and at least a lower bound on the isoperimetric numbers of each topology. Remember that it is dynamic, so the topology may be changing, but a lower bound on each topology occurring in the network of the isoperimetric numbers is known. What we show in this work is that randomized network average consensus is not possible without a known number of distinguished nodes that we will call supervisors. Similar observation has been proved for deterministic counting, where counting problem is finding a network size, which is equivalent to average. It has been shown. Therefore, our claim is true for all algorithms for network average consensus, not only randomized. Given that, we present an algorithm for network average consensus where we assume the presence of some number of supervisors. We call it L, and that number is known to all nodes. And we call the algorithm isoperimetric scalable coordinated anonymous local aggregation. The name is long, so we will call it iSCALA. And the algorithm is based on a methodical multi-counting algorithm, a previously known algorithm to compute this network size in the same setting. But iSCALA is designed to use the isoperimetric dynamicity that is known to improve the time complexity. Indeed, the MMC, the methodical multi-counting algorithm, and other counting algorithms are inefficient for practical networks with good expansion because they have been designed to cope with worst-case scenarios. Therefore, in some sense, iSCALA adapts to changes in the topology. We also analyze, of course, the iSCALA algorithm for adversarial and various stochastic topologies, and we carry out, to complement that, the theoretical study, we carry out thorough simulations. Let me briefly describe the impossibility result. We have two theorems. One shows that for any constant c, there exists some network, anonymous dynamic network, with some supervisor nodes, without supervisor nodes, such that there is no randomized algorithm that with constant probability, even with constant probability, solves the problem, even knowing a lower estimate of the isoperimetric number. And we prove a similar claim for when we do have supervisor nodes, but their number is not known to network nodes. The idea of the proof is quite technical. The idea of the proof is to show a carefully designed network that has constant isoperimetric number, both globally and locally. Therefore, we can show that with constant probability, any algorithm reaches a termination configuration locally before receiving any global information, before having time to receive information from other areas of the network. With respect to the design of iSCALA, the structure, I'm going to describe the structure and briefly the main idea. The structure is the following. The algorithm is divided conceptually in epochs. In each epoch, nodes try an estimate of the network size. Having the network size, we can obtain the average. So we focus on computing the network size. For each estimate of the network size that we call k, the nodes initialize some value, local value called potential. The supervised nodes initialize that value to L, the number of supervisors, and the supervisor nodes initialize that value to 0. Then for each epoch, we have a number of phases during which at the end of each supervisor nodes will remove potential from the consideration. So remember, all the nodes have some potential. They will be sharing it iteratively, and at the end of each phase of sharing, supervisor nodes remove potential from the consideration to a local accumulator. Within each phase, we divide it conceptually in rounds that are used to average the current potentials. So for instance, in the illustration on the right, we have a network with one supervisor depicted in black and 6 supervised nodes depicted in white. You see that the supervised nodes have some potential, full potential, which is what we initialize to L, and the supervisor node does not have any potential. Then after some rounds of sharing the potential among neighbors in a gossip-based fashion, all nodes have more or less the average of the total potential in the network. Therefore, at the end of these rounds, at the end of the phase, the supervisor node removes the potential to a separate accumulator and repeats for the next phase. All nodes repeat the procedure, averaging again. At the end of the phase, the supervisor removes the potential, and after enough number of phases, they keep doing that. After enough number of phases, the supervisor has removed pretty much all the potential from the network. The supervisors decide whether the current estimate k is correct as a value of the number of nodes in the network or not, according to this potential that they have in the accumulator. If they detect there are a series of alarms in the algorithm, if they detect that the estimate is bigger or equal than the network size, they are able to notify all the other nodes by simply broadcasting the news. If they don't receive any notification, nodes assume that K is still low, and they move to the next epoch, trying the next value of K. That's the main idea. There are lots of ingredients in this algorithm. And we also carry out the analysis for a variety of topologies. For adversarial topology, we obtain an upper bound of n to the 3 plus epsilon. Epsilon is any constant bigger than 0. N to the 3 plus epsilon divided by the number of supervisors and the lower bound of the isoperimetric number squared. This upper bound improves over the previous counting algorithm for isoperimetric numbers that are at least 1 divided by square root of n. And there is a lower bound of 1 over n, so this is up to constant. This is a large range of isoperimetric numbers. And this is true even if only a lower bound on the isoperimetric number is given. If we have more precise lower bounds for each change in topology, then we can obtain better running times. And for stochastic network models, we also upper bound the running time of iSCALA, and you can see in the table a variety of upper bounds for different models of random graphs like Erdős-Rényi, random geometric graph, Watts-Strogatz, Barabasi-Albert, and so on. We complement our theoretical study with simulations, and the goal of these simulations is to evaluate a hypothetical early stopping centralized version of iSCALA against the upper bounds in the analysis. So what do we mean by that? We run iSCALA centralized because it's a simulation, we can do it, and we do early stopping of the algorithm. Every time that nodes detect that the estimate of the network size is low, or whenever they have reached to the conclusion that the estimate is correct and we have reached the final count of n, the counting of the number of rounds in the simulation is stopped. And we show that even with that hypothetical, highly optimistic version of iSCALA, the upper bounds in the analysis are close, showing that indeed the theoretical analysis is close to practice. The inputs evaluated in our simulations are for random graphs. We try these 3 different models that I mentioned before, and we also try deterministic topologies that entail worst case and best case for gossip-based algorithms as iSCALA, where we share these potentials, like trees, stars, and paths. The supervisor nodes were located at random in the networks, and all topologies are t-stable connected, meaning for t rounds, the topology doesn't change. Or if you want, with a frequency of t, the topology changes. And we try different values of network size from 6 to 48, different number of supervisor nodes from 1 to half of the nodes. The frequency of changes in the topology, we tried changing it every round and every 100 rounds. And we use a lower bound on the minimum isoperimetric number for these topologies. And we instantiated a variety of parameters that each of these random graph models have. We measured the average behavior over multiple executions of the simulator, and we obtained similar behavior for all our cases. In these plots, you can see some examples. For instance, in the top left, you have for one stable networks, meaning topologies that are changing in every round. The topmost line corresponds to the methodical multi-counting theoretical upper bound, the black line. The line that follows going down, the red line, corresponds to the upper bound of iSCALA algorithm when the isoperimetric number is constant, as in these cases. And you can see the gap between both running times, how iSCALA improves over multi-methodical counting. And then the lines that follow continuing down correspond to the topologies evaluated in our simulations with this early stopping centralized version of iSCALA. What these plots show is that even with this highly optimistic implementation, the running time is better than the theoretical iSCALA running time, but close, meaning that our upper bound is tight for this choice of parameters and topologies, practical topologies. Similar observations can be done, for instance, in the bottom right, that corresponds to networks that change every 100 rounds. In this case, the x-axis is the number of supervisor nodes. So we can see here the behavior of the algorithm as the number of supervisor nodes increase. And again, the topmost line corresponds to the methodical multi-counting algorithm upper bound. The red line that follows going down is the iSCALA theoretical upper bound for constant isoperimetric number, and the rest of the lines below correspond to the topologies evaluated. And again, the same conclusion. We see, as expected, that the running time reduces with the increasing of number of supervisor nodes. But what is more important is that our experimental evaluation shows that our theoretical analysis is tight with respect to many practical networks, many practical applications. Are there any questions?